Okay, I think we can start. Hi everyone, welcome to the 93rd Stanford MedAI Group Exchange session. This week we have Yunhe Gao from Rutgers University here with us to talk about his work on universal medical image segmentation. Yunhe is a fourth-year PhD candidate in the Department of Computer Science at Rutgers University. His research focuses on computer vision and medical image analysis. He is also broadly interested in AI model robustness, data efficiency, and their applications in the machine learning and healthcare domains. Thank you very much for joining us today. Before we start, do you have any preference on how you would like to take questions?
Yeah, I'm open. You can interrupt me if you have any questions. I'm open to that.
Okay. Thank you very much. Let's try to make the session as interactive as possible. And without further ado, let me hand it over to Yunhe.
Okay. Hello, everyone. I'm Yunhe Gao, a senior PhD student from Rutgers University, and my supervisor is distinguished Professor Dimitris Metasas, who has been working on medical image analysis for over 20 years. I'm very glad to have the opportunity to present our work in this seminar, and the title of my talk is Toward Universal Medical Image Segmentation, Challenges and Opportunities. So let's start from the background and our motivations. Data is the fuel that powers more than AI, and the data, we see data as the backbone of the data-driven AI, because the scale and the quality of the training data decides the upper limits of a model. And the larger training data and the larger models are mutually reinforcing. That is, larger training data sets usually facilitate the training of larger models. And the bigger models can capture more complex patterns and has better generalization and robustness. Here's a figure from a paper from OpenAI's illustrating the scaling laws of neural language models. And here the x-axis is the number of parameter of models, while the y-axis is the testing loss. The lower, the better. And the color of these curves indicates the size of training data. The darker one, the blue one, means smaller training data, and the brighter one, the yellow one, means larger training data. We can see that larger models usually have lower testing loss, means better generalization. But if the training data set is small, larger model, the performance gain saturates very fast, and even have overfitting issues for the large models. But if the training data set is large enough, the larger data set has very low testing loss and very good generalization and robustness. From this figure, we can see that maybe we do not need to design fancy models, just collect large scale and high quality data, and we can simply scaling up the size of some well-established models, and we can get very good performance. So this data-driven AI paradigm has leading to many successful works. For example, in the NLP field, the GPT theories, they are built on straightforward transformer architectures with no task-specific architectures or objectives. By leveraging the large data and the large models, like the GPT-3 was trained on 300 billion training tokens and 175 billion parameters. The GPT-3s can deal with a bunch of tasks in zero-shot or few-shot setting. Similar happens in the vision domain, like, for example, the representative work segment anything. It was also built on very simple backbones using the VIT backbone, and it can deal with different segmentation inputs with input prompts. And the SAM model was trained also on a very high quality and large scale data sets with over 1 billion object masks and 11 million images. So from these two examples, we can see that using simple established backbones like the transformers in GPT or VITs in SAM, or even UNet like in the stable diffusion, we can scale those well-established model up and then use some large-scale and high-quality data for training, and we can build some generalizable and robust models. So after seeing those successful works in other domains, let's go back to medical image analysis. Data is actually a long-standing challenge in medical image analysis. Unlike nature images, where everyone can take photos with their phones, medical images requires professional medical equipment, making the data acquisition very difficult. And also the annotation requires expert knowledge. Like people without long-time professional training cannot do the annotation. Also, the privacy issue is a big issue because it makes it difficult to get access to large-scale sensitive patient data. Besides these issues, the current clinical workflow usually focus on some disease analytics and diagnosis, making the current medical imaging datasets where the modality and the annotations are strongly tied to specific clinical objectives. This figure from the medical image decathlon shows this phenomenon. Like each modality has its own strengths. For example, MRI is good at soft tissue contrast, and thus the brain or heart related disease usually use MRI, while the CT images is faster and good at bone visualizations and has its own application in like abdomens or something like that. So this clinical workflow leading to a lot of separate data sets for different clinical objectives, while each data set has very limited quantity of data, like tens or hundreds of data. So in this current paradigm, or we name it as a traditional paradigm, we usually design some like task-specific network architectures. Like what we've done in our previous work, we designed a Madformer, a transformer model, and the models are trained on this separate data set to solve a very specific task. For example, we need a model 1 to train on the brain data to solve brain tasks, and train another model in the liver data to solve liver-related tasks, and another model for the heart. So this traditional training paradigm has several limitations. First, it's very difficult to further scale up the data set size for a single task. Also, because data are coming from the same clinical targets, usually have some similar distributions, and thus making the trained model to have very limited generalization. Furthermore, the separate models cannot leverage the synergy between tasks. Therefore, the current paradigm making it impossible to build robust medical AI similar to what we've done in NLP and general vision tasks. So to solve this problem, we are interested in how humans are trained into radiologists. Therefore, we look into the curriculum of some medical schools in diagnostic radiology. For example, in the US, there's accreditation council for graduate medical education. This ACGME program provides a guideline for diagnostic radiology education. So we find that besides some necessary medical knowledge, the guidelines specify that every radiology resident must meet some minimum volume across a diverse array of imaging modalities and examinations. For example, they need to read over 1,000 chest X-ray and hundreds of brain MRI or abdomen CT images. Besides this, we also find that the ACGME guideline emphasize that exposure to a range of clinical subspecialties through clinical rotation is very important. This includes like abdominal, cardiac, and something like that. So we found that during this process, some essential prior knowledge about the target region is gained for interpreting the subtle patterns. And these guidelines clearly highlights that the importance of engaging with broad range of body regions, imaging modalities, and tasks for radiology residents. Thereby, this motivates us to design a similar learning paradigm for machine learning models. So in our work, we explore an universal medical image segmentation paradigm whose goal is to learn from diverse imaging sources. For example, in the traditional paradigm, we train separate models for each task. We needed multiple models to solve different tasks. And in the proposed universal paradigm, we train a universal model that learns from a diverse range of medical data sets. And it can perform multiple image segmentation tasks within the same model. So the training data sets can vary. They can have different clinical targets, they can have different modalities, or they can from different body regions and annotation categories. So there are multiple merits of such universal training paradigm. The first is by learning from diverse medical image sources, the models can learn robust and generalizable and transferable feature representations. Moreover, although different body region and the different modalities shows very different appearance, human bodies are actually building on similar structures like bones, muscles, or some soft tissues, and so on. So the universal paradigm can utilize the synergy between these different clinical targets. Besides, with this universal paradigm, we can effectively combine a wide range of medical imaging data sets into a larger scale training set with a very low cost. So we can scale up the training set size very efficiently. And at last, we can use a unified model to solve multiple tasks instead of use multiple separate models. Yeah, well, although this our ultimate goal or the objective of the universal medical image segmentation is very promising, there are actually several technical challenges need to be addressed. For example, the first one is the partially labeled problem, because each image dataset has different and incomplete ROI annotations because they have different needs and clinical objectives. For example, in the dataset 1, both dataset 1 and the dataset 2 are CT abdomen images. But the dataset 1 focus on 15 organs, while the dataset 2 only focus on the liver and liver tumor. So they have different annotations. All of them are incomplete. And the second challenge is that the class definition can be different or even contradictory. For example, for the liver in the dataset 1 is annotated as a whole organ, while for dataset 2 is designed for liver tumors. So the same liver region is separated into liver and the liver tumor. Besides the partial labeled problem, there are also other challenges caused by the heterogeneity in the medical image data. For example, data with different modality or data from different body regions shows very different appearance and distributions. Such heterogeneity in the data cause challenges in the universal paradigm. So because of these challenges, the joint learning from such heterogeneous medical image datasets has long been considered as not viable. So in this work, to handle this partially labeled problem and the heterogeneity in the data, we propose our solution with context prior learning. Here is the figure of our framework, and we name our methods as Hermes. So the core idea of our method is the joint learning of a shared backbone for all tasks and some task-specific context knowledges. During inference, we can use the learned context knowledge to guide and help the model to perform assigned tasks. So let's go into the details. The inputs are images from different data sets, which can have different annotated categories and imaging modalities. Our methods consist of two main components, the backbone and the task-specific context prior pool. The backbone, which is the green block here, is shared among all the tasks. It includes encoder and a decoder. The role of this backbone is it works as a universal feature extractor whose goal is to encode the images into meaningful feature representations. And this backbone can be any segmentation models like UNet or other transformer-based models. To enable Hermes to handle various tasks and the different data modalities, we designed two types of priors within the context prior pool, including the task priors and modality priors. These priors are implemented as learnable tokens like this. So now let's consider how a doctor diagnosing a...
So sorry, Ian, like I have one quick question. So when you say like task prior, task priors are kind of like one-to-one mapping between your task and the data set, right?
No, like for example, there are 15 organs in dataset 1, then there are corresponding 15 task priors.
Okay.
Yeah, and the dataset 2, it has 2 tasks, and it has corresponding 2 task priors.
Oh, okay. Okay. So task priors are based on the not only the data set, but also the labels within the data set. Okay.
Yeah, it's more fine-grained. It's related to the targets. And the modality priors is for each modality. For example, we have CT and MRI, we have 2 priors, modality priors.
But even if the MR can have like different sequence, right? So are you also...
that's true. So for now, we do not treat different MRI sequence as different modality.
Okay.
Yeah.
And you know, if some task is shared between 2 data sets, would it still get like 2 different task priors, or it would be the same?
It depends. For example, if we are sure that the tasks in the annotation of the same object, like the liver, they are exactly the same from different data sets, we treat them as the same task prior. If they are different, maybe they have some like different preference, we treat them as separate tasks.
Okay, makes sense.
Yeah. So okay, so let's start. Let's think about how a doctor diagnoses a scan. For example, there are a few factors that doctors already know. For example, what is the current objectives? For example, what we are interested in, like we are interested in liver or tumor or kidneys or something like that. Another factor is that the doctors know.
I think we have a question in the chat. How do you come up with the task and modality priors? Are they manually designed?
How do you come up with them? They are not manually designed. They are like initialized as learnable tokens, and these tokens are learned with the backbone and trained jointly with the backbone through the gradient descent.
Essentially, they are learnable priors.
Yeah, they are learnable tokens, similar to the vocabulary in language model.
Okay.
Yeah, they are randomly initialized and learned.
But do you know that how many prior available? Like in your example, the first task, you already know that there are 15 organs. So is this a kind of a known kind of parameters for the model?
Yeah, actually, this is known because we do not need to assume we do not know that, because when a doctor diagnoses a disease, they know what organs they are interested in, right? We do not need to assume we don't know that.
Okay.
Yeah. Yeah. So like when doctor diagnoses a scan, they know what organs they are interested in, and they know what modality that scan is, right? So we are doing the similar things as a doctor, because when doctor know these factors, they can use their associated knowledge of the targets and the modality to help diagnosis, like what a liver looks like in a CT image, some prior knowledge like this. And the proposed method Hermes use a similar strategy, and it used the two known piece of information as an oracle or as a guidance to select and combine the modality priors from this pool. So, for example, let's use the dataset 2 as an example, using the liver and tumor and the CT modality. So Hermes will actually select the corresponding task priors from this task prior pool, the blue ones for the liver and tumor, and also select the CT modality priors. And Hermes will concatenate those priors together into a token sequence. And
sorry, like I have one quick question here. It is a 3D model, right? It's not a 2D.
It's a 3D model, yeah.
Okay.
Yeah, it's a 3D model.
Thank you.
Yeah.
Because otherwise, like probably, like if you're looking at tumor, probably if it is 2D, you cannot see tumor in all the slides. Yeah. Okay.
Yeah. But actually, it's not a problem for even 3D. You may not see a tumor, right?
Yeah, but still, like if when you are doing like the bottleneck embedding, you should have some information about that tumor in your bottleneck.
Yeah. During training, that's true. Yeah.
Okay.
Yeah. So after we select the task priors and the modality priors, we concatenate them together into a prior token sequence. And the prior fusion module here is actually a bidirectional cross-attention module. It takes two inputs. The first one is the prior token sequence and the image feature map. This prior fusion module will exchange the knowledge between the priors and the image features, such that the knowledge in the context priors can be injected into the image feature. And the priors also aggregate instance level or image level informations to generate discriminative posterior prototypes. And these posterior prototypes are used to obtain the binary segmentation of the targets. For example, in this dataset 2 as an example, we have two task priors, one for liver and one for tumor, and one modality priors for the modality. In the prior fusion, these three priors are doing like cross attention with the image features. So during this fusion process, the context knowledge will be injected into the new feature map, and also the liver token and the tumor token will aggregate information from the image features, and we use those. We call this updated priors as posterior prototypes, and use this one to do like dot production with the output of the decoder and to get the binary prediction here. And why we use the binary prediction here instead of softmax multi-class segmentation is because the number of categories in different datasets are different. So we cannot simply use a softmax to do that. So we use treat every targets, every organ or tumor or every object as a binary segmentation task. And also to boost the performance, we also implement the prior fusion in multi-scales, not only in the lowest resolution in the backbone, it was implemented in multi-scales. So far is the method details. So any questions regarding this method?
Yes, I have a question about the binary predictions. So is this in terms of in the pixel level?
Yeah, it's a pixel level. So basically,
Okay.
this one, the dimension of the output is the same as the image.
Okay.
And the channel, we will output each, like multiple channels for each targets.
Okay. And previously, before you introduced this model architecture, you said it's a universal model. So
Yeah.
does this mean that, for example, on the left you have multiple tasks? Do you train a single model on all of the tasks, or you train an individual model?
No, it's one model for all. Like although we use, like, we ensemble all this data set into one large training data set, and we can, like, we do some engineering tricks to make the model can take the combination of different samples from different data sets as input for training. So
Okay.
it's actually one model for all.
Okay. And I think Amara has asked this question before, but I just want to clarify that, for example, the task 1 and task 3, the first one has 15 organs and the third one has 5 organs. What if they have overlap? Will you have one organ for each data sets, or you will have one organ for work for all of the data sets?
So actually, because different data sets has their own focus, right? Their annotation, preference or definition of class may be different. So if we are sure that these two data sets have the same definition, we'll like merge them. Like if they both contains like a liver, we'll merge them. If we know that we don't know that they have exactly the same definition, we will treat them as separate. For example, for data set 1, we have one liver, and for data 3, we have another liver, because it's yeah.
Okay, thank you.
Yeah.
There's one question in the chat as well. Could you expand on using multiple scales? Yes.
Regarding the multiple scales, like we are doing the similar multiple scales like in like Deep Lab, something like that. We use the feature pyramid. Like we use the prior fusion in different resolution in the backbone. Like the UNet has 4 or 5 times of downsampling, right? So we implement the prior fusion and the context prior pools in 3 resolutions. Did I answer your question?
Yeah, thank you.
Okay.
With respect to the learnable tokens, do you actually enforce certain things to make sure that some tokens learn the task-specific priors and some tokens learn modality-specific priors? Like, how do you exactly enforce those learnable tokens actually learn what you mean them to learn?
Yeah, actually, for the task priors, we enforce it to learn, like we enforce it to learn exactly what we want it to learn, because during the prior fusion, the task priors are aggregate information from the image feature maps, right? And we got this one, and we use this one and project it with an MLP, and use this one to get the posterior. Basically, this works like the classifier, the weights in the classifier. So we use, which has like corresponding, like this posterior has corresponds to the previous like liver task prior. So they have correspondence, and we can make sure that the liver task priors learns something about liver, and I can show that in the following visualization. For the modality, actually, we do not enforce anything about it, and we just treat it as some modality-specific parameters.
I see. So, like with respect to the tokens, there is not any difference between the task tokens and the modality tokens, if I'm not wrong, or
they are a little bit different, but kind of similar. The only difference is like we have one token for each target. For example, for liver, we have one token. But for modality, because like the modality is a more like a complex concept, right? Each modality consists of a lot of variants. So we use longer sequence to each modality. So in our implementation, we use 10 tokens for one modality.
Okay.
Mm-hmm.
I have one more question about the datasets.
Mm-hmm.
So when you combine all of the datasets, do you observe that some datasets might be more than the other, and will that affect your result?
Yeah, that's actually I would like to talk in the later slides. So
thank you.
yeah, there are actually different sites because like we use 7 data sets for upstream training, and someone is larger, like few hundred, and someone is smaller, like tens, like 30. So we do observe that, and we use some sampling rates on this different data set. So basically, for smaller data set, we have larger sample rates, and for larger data set, we have smaller sampling rate to kind of balance between data sets.
And does that strategy affect your result? Like if you don't do that, or compared to you do that?
Yeah, it will impact the final performance a little bit, but not a lot.
Okay, thank you.
Yeah, any other questions?
I have a question about the modality prior. So modality, is that also like the learnable parameters, for instance?
Yeah, both task and modality are learnable parameters.
And I was wondering, so how is there any specific strategy for the initialization for the modality?
We do not do specific. We use Gaussian initialization. Randomly initialize them and learn through the training. Yeah.
Okay. Yeah. Thank you.
Mm-hmm. What are the binary prediction? Binary prediction means it's 0 or 1. Like we do not do multi-class classification. We do like we output multiple channels from the model, and each channel is corresponds to a target. And in each channel, its output is either 0. It predicts a logit in the range of 0 to 1. So if the value is larger than 0.5, we treat it as foreground. If the value is lower than 0.5, we treat it as a background. Yeah, that's binary.
Does that mean that you have multiple binary segmentation heads and that you stack them up at the end, like linear layers at the end, or? Actually, no, because you can see that we do not have multiple heads, because the heads is actually the posterior prototype. You can see that by selecting the task priors, we decide how many targets we want to segment, right? So the T, like the T means how many task priors we are using. And actually, this is a dynamic process. You can choose, for example, in the first inference, you can segment like 15 organs. In the second inference, you can segment like 2 targets. And also you can, in our implementation, we also use some tricks to combine different data sets together. So we actually pad something, because the first data set has 15 organs, the second one only has 2. So actually we have some like null tokens to pad the second data set to have the same like shape with the first data set. So such that we can like during one inference, we can do different kinds of segmentation with different data sets. Is that clear? Yes, thank you. Oh, another question. How do you deal different spacings between these data sets? Do you?
Oh, yeah. we use standardized pre-processing, like we resample all the different data sets into the same spacing, and also do the same normalization. Like for the CT, we do a window and normalize it into 0 to 1. Oh, actually not. We do the windowing and also then do the subtract the mean and divide by the standard deviation. And the same thing for the MRI, like subtract the mean and divide by the standard deviation. Yeah.
All right, thank you.
Do the task priors remain same for every scale in the feature pyramid, or do they need to be retrained? Actually, they are different. Like, because in the feature pyramid, they have different number of channels, right? In the lower resolution, you have larger channels. In the shallower layers, you have like smaller channels. So actually, the priors we implement with different priors. So they are trained together, but they are different. There's no need to be retrained, but they are different. Yeah, if no more questions, I can go to the experiment part. Oh, but when you combined all the data, actually during training, we combine all the data. Like for example, during training, we have a batch size of like 16. So we need to sample 16 volumes, like 3D volumes from all these data sets. Actually, we can sample randomly. We just randomly sample from this data set to get a 3D volume for training, and we can combine those 16 mini batch together for same like training iteration. Task read. No, not the same. Like actually, as I explained before, we use some engineering tricks to make they are the same. For example, we for the dataset 1, we have 15 organs. This is the largest data set, the most class we have. So we also introduce a null, like an empty token, task token. So basically, we can pad the second data set with some null tokens to make sure it's the shape of the task priors are aligned with the first data set. Yeah, but during inference, we do not need to do that. We can we do not need to use the null token for that. Okay. If no questions, I'll go to the experiment parts.
I have one more question. I'm sorry. So what did you actually achieve by incorporating this prior fusion inside the encoder decoder? And have you tried to do away with the prior fusion and then compare the two frameworks?
Actually, without prior fusion, I don't see how you like introduce your task priors or modality priors into the framework.
No, so in that case, there will be no priors in that case. Yep.
Yeah. Without this, because different data sets has like different categories, right? Without this design, you cannot train with different data sets, right? Yeah, this task prior is what we designed to deal with the partially labeling problem, right? Yeah, and one key advantage of this design is the selection of task prior is adaptive. You can even like combine the different class from different data sets during the inference time. So it's more flexible.
And how do you manage the different modalities? So the way you did with task prior, you pad the zeros for the for the rest of the tasks. So how do you manage? So are there fixed modality priors? And then
yes, in our experiment, we only have a CT and MRI modality priors because the data sets are selection. So if the CT data comes in, we use the CT prior, and if MRI comes in, we use the MRI prior. Okay.
Thank you.
Okay, I'll go to the experiment. What the results looks like. Okay, let's go to the experiments part. So to evaluate the effectiveness of this challenging universal paradigm, we curated our dataset with 3 factors, basically the body region, modality, and the clinical targets. So we primarily focus on the abdomens and select 1 dataset into the thorax. And the most datasets are focused on CT and with 2 from MRI. And for the clinical targets, we mainly focus on the organs, while 2 has tumors. And we also evaluate our methods on 2 downstream tasks. So let's see the results. So in this radar plot, we show the comparison between the universal paradigm and the traditional paradigm. We also show that the comparison between other multitask learning methods with the Hermes under the universal paradigm. So the number here is the DICE score, the average DICE score. The red curve here is the traditionally trained ResUnet, and it is trained separately for separate data sets. We can see that methods trained with universal paradigm consistently outperforms the traditional paradigm, like in terms of average performance over all data sets or all class, or even on the difficult class. And in the difficult class, we define it as the DICE score lower than 80. And besides, we also find that the joint learning shows notable improvements across modalities, body regions, and the targets. Like, although most training data sets are from CT modality, we see that there is a significant improvement in terms of MRI modality. And for the regions, most of the data sets are from abnomens, and we also see improvements in the task in the thoracic region. For the targets, most are organs, and we also see improvements in the tumor. Yeah. So among the universal paradigm, the Hermes also outperforms other multitask learning methods.
In this case, difficult classes when using with DICE score of less than 0.8, do the same type of classes are difficult for
we
different
use
models?
We use the NUnet, the performance of NUnet to define difficult class.
Okay.
All the models use the same difficult class.
Okay.
Because I think like one problem is like you are showing here the mean DICE score, right? Do you have like the standard deviation for all these models? Because I know that it is very difficult to represent it in one figure, but just out of curiosity.
We do not provide standard deviation because our training set is very large. To train such a large data set, it takes a lot of computation and the time. We do not have the time to run multiple runs.
Okay.
Yeah. And another interesting observation is that we find that the universal paradigm significantly improves the model scalability. Like in this experiment, we use the regular ResUnet as the base, and we scale it down or scale it up into a smaller and larger model. Like we change the number of layers, or we change the number of channels of the ResUnet to result in a small version or a large version of the model with different number of parameters. So here, the y-axis is the average testing dice score over 7 datasets. And we can see that in the traditional paradigm, because each dataset has very limited number of data, and increasing the model size has limited improvement. Because the dataset is small, increasing model size might introduce overfitting issues. But in the universal paradigm, the model can see, because it is trained on more diverse data sources, and the larger models has better capacities to learn more robust and generalizable representations. So the proposed universal paradigm can break the limitation of traditional paradigm. And besides this upstream comparison, we also do evaluations on the downstream transfer learning and also incremental learning setting. So we use the pancreas and the tumor dataset from the medical segmentation decazone. And for the transfer learning setting, like all model parameters are fine-tuned with the downstream data. And we compared with some established settings in the transfer learning, like training from scratch or transferring weight from a single data set, like transferring from the MOCT, which is the largest data set in our upstream training, or from the KITS, which has the annotation for kidney and tumor. And we also do the experiments under different data ratios, like 1% means 2 scans, and 10% means about 20 images, and 100% means about 214 images. And we can see that the proposed Hermes has much better transfer capabilities compared to training from scratch or transferring from a single data set. Like if we have only with the half number of downstream data, the Hermes has outperformed the training from scratch with the full data or transfer from a single model, from single data set.
So when you say Hermes, it's actually the model trained on the 7 data sets, right? The combination of 7 data sets. So have you?
Go ahead.
Yeah, have you just compare like just train the Hermes on the downstream task without the pre-training on the combination of 7 tasks?
You mean train from scratch, right?
Yeah, train Hermes from scratch on the downstream task.
We didn't do that, but we've done this experiment using a single upstream dataset.
Okay.
Like upstream dataset, we do that with LITS and KITS to train Hermes from scratch with a single dataset. It actually has a similar performance with ResUnet with its backbone.
Okay.
Yeah, and and also we test on the incremental setting, which is a more challenging setting, because incremental learning requires learning new classes without interfering with previous ones. So in this setting, we fix the backbone and the context priors for all previously trained classes, and only train the new task priors for the new classes, named the pancreas and the tumor. So we can see that under the more challenging incremental learning settings, Hermes shows better performance than the traditional, like even the full fine-tuning in the low data regime, like under 1% or 10% downstream data. And even under 100% downstream data, Hermes shows very good performance compared with full fine-tuning. And this result demonstrates that the diverse upstream training makes Hermes learns very generalizable representations. Even the backbone is fixed. We only train the task priors. We can get a very good performance.
Could you explain what's the difference between transfer and incremental again?
So for transfer learning, basically we fine-tune all the parameters. So because transfer learning, we do not care the performance in the upstream tasks, right? We only care the performance in the downstream task. In the incremental learning, it's more challenging because we also care about the upstream performance. We want to model to not be affected the performance on upstream with the new class from the downstreams.
Okay. So are you saying that you're in the incremental settings, you also train Hermes on the downstream task, but you evaluate on your upstream task?
No, actually, because the backbone and the upstream tasks priors are fixed, so it's not the performance on upstream will not be impacted. Because the parameter in the backbone and the task priors are all fixed. We only train the new task priors.
So in this case, except for the task prior learnable parameters, nothing is changing.
Yeah, modality prior is not. Yeah, modality prior is not trained, and all the backbone, all the things are fixed. Only train the new task prior.
Okay, and how do you control this in your baselines, clip-driven and DoD-net?
Oh, actually, because DoD-net and the clip-driven are all trained in the universal paradigm, so they also have some strategies to inject those task-specific informations. So we are doing the similar things with Hermes.
Okay.
Okay, let's continue. So we also, besides this, we also evaluate the generalization capabilities in the generalization setting. So in this setting, all the model parameters are not fine-tuned; they are all fixed. We directly make inference on the new dataset, and because the struct-seg dataset is the one dataset in our upstream training dataset, and it has it is from the thorax region, and the sexor dataset is another similar dataset, but never be used for the upstream training, and they have 3 category overlap, including the esophagus, heart, and trachea. So we can directly make inference of what we trained from the struct-seg to the sexor. So because of the distribution shift caused by centers or scanner vendors, we can see that the traditional trained ResUnet, the red one, has compromised performance. And the universally trained Hermes, the green one, shows better robustness against the distribution shift. Yes. And we also show do the visualization of the activation map of the task priors. We can see that as someone asked before, that how do we enforce the task priors to be associated with some targets? So we can see that the task priors really has very high activation on the corresponding target regions. Even on very small objects like aorta or something like adrenal glands, the activation is very accurate. So to conclusion,
sorry, is it the visualization of the prior, or is it like the GradCam on the input slice?
It's actually like this. So we visualize the posterior on this. That is we visualize the similarity. We compute the similarity between the posterior prototype with the feature map here. So the higher similarity means a higher activation.
Higher activation. But then does it? Okay, your model is 3D. Otherwise, I was thinking like, what if the slice looks very different? But since it's 3D, you don't run into that.
Yeah, because we are using like sub-volume inference. You can see the board artifact like here, because we are doing 3D inference.
By the way, what's the sub-volume size in your experience?
128 by 128 by 128.
Okay.
How many parameters are there in Hermes R and Hermes M? Oh, we have, I kind of forget, we have included this in our appendix. It's like let's see, like 40 million, about 40 million for both Hermes R and Hermes M. I think Hermes R like should be larger, like 60, and Hermes M should be something like 40. Yeah. And to conclude this our work, we introduce a universal medical image segmentation paradigm that learns generalizable and transferable representations from diverse medical tasks. And following this paradigm, we propose Hermes, an oracle-guided context-prior learning approach to tackle the multiple challenges regarding the annotation labels and the image heterogeneities. And we demonstrate extensive experiments with Hermes to show the superiority of the universal paradigm in both upstream and downstream tasks. And I also summarize some like challenges and opportunities, because our work is an early exploration in this universal paradigm. There are still a lot of challenges and opportunities. So, for example, like how to deal with highly imbalanced data. So currently we do some simply strategy like sampling rate, but we expect there would be more adaptive way to solve that. And also, what will happen if we incorporating more diverse data modalities, more tasks, and more anatomy structures? Can we build a large medical image foundation model similar to segment anything? And there are also challenges regarding how to make use of unlabeled data, because in our work we use supervised learning. It would be beneficial to leverage more unlabeled data, or make use of the partially labeled images in other data sets. There are also some kinds of long-term opportunities, like how to integrate more medical prior knowledge into the model, because in our work we let the model to learn prior knowledge from the data, like learn the task and the modality priors from data. It's an interesting topic to introduce more prior knowledge into the model. And also it's interesting to see if it's possible to align the large medical vision model with large medical language model. In this way, we may be able to make more use of medical knowledges like written in text to help the diagnosis. Yeah, that's all for my talk, and thank you for your listening. Our paper is here and the GitHub is here. Yeah, thank you.
Thank you very much, Yunhe, for this very interesting presentation. So everyone, let's give our speaker a round of virtual applause. And then if you have any questions, please feel free to ask.
Yeah, regarding the codes, we just finished the rebuttal and we will release the code very soon. Yeah, besides, I'm actively looking for my career opportunities like research scientist or postdoc positions. If anyone who are interested or have related positions, please feel free to reach out. Thank you. The training weight is also going to be released. We prepared for the ResNet and the Medformer free training weight. We'll release it.
So we are almost out of time. If you guys have any questions later, we can put you in touch with the speaker. Also, this talk will be uploaded to the YouTube maybe in the next couple of days. If there are no other questions, so thank you very much, Yunhe, for joining us today, and best of luck for your future. And
Thank you.
everyone,
Thank you very
we'll
much.
see you hopefully next week, same time. Thank you very much.
Thank you very much. Bye, everyone.